little back away on mine.
My two favorite things, laying down and being surrounded by water.
Last time I took a bath was out of necessity because I physically could not stand up to take a shower.
Wow.
Did you have like a broken leg?
No, I had a series of just like reactions to the medication, and so all my joints swelled up, so I couldn't walk and stand very well.
We heard all about inflammation yesterday, talking about your swelled joints. We were at the fetal alcohol syndrome, and we were hearing about how microglia play an important role in fetal alcohol syndrome. So swelling is everywhere.
Yes, it is.
Good morning, Vanessa.
Good morning. Instead of doing the TED last night, I watched 2 episodes of X-Files.
Oh, I thought you were going to say you watched 2 episodes of other TED Heads.
I wrote part of my lit review. That's what I did instead.
You what?
I wrote part of my lit review using the
Oh, good.
I was like, cool, now I have more time to do this.
I prefer being in every class.
You get one carryover.
Yeah,
So we meet 14 weeks. We have something like 3 TED Heads a week in each of the classes. And one of them is a duplicate.
Yay.
Yay. It's a false positive.
Got up this morning and I like, because I left like the technical part of this morning, so a lot of times when I get up early in the morning, I
Hi, Jake.
find these guys early, which is weird because I'm not a morning person. So I was like, I'm going to leave this technical stuff until the afternoon.
We do have 2 handouts on the front table if you'd like to grab those. One is an assignment, and one is just the TED Ed questions for today. Sometimes, I think we do better if we have the TED Ed questions right in front of us.
I mean, I'm not done with it, but the part that I've written is only 6 pages. I don't know.
Right down 22 pages.
Oh my god. I think the majority of mine has to do with one thing. And like, I remember very first couple of times I just wiped it out. And then that's the order of things. Yeah, I'm probably gonna write the S&P.
They're only single.
Oh, some of them came out only single-sided?
Yeah.
Oh, okay.
Thank you so much. I owe you one.
Yeah, we all got way more complicated passwords too, right? Yeah. Uh-huh. Interesting thing about that, neurologically, that there's considerable evidence that the way we store simple numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, is actually distinct from the way we store simple letters, right? So typically when we learn to type, right, we go full steam ahead with, a bunch of letters for the words, and then maybe all of a sudden we have to insert one number, but it's a number entire. It's very rare that we would ever have to do a bunch of letters and numbers interleaved, right? Mm-hmm. So it demands a lot of thinking. Good morning, Victoria.
I have copies of 2 surveys that I'm using, but I need to.
Victoria, we do have 2 handouts over on this side. 2 handouts.
go through the summer, and where did you do that? Like,
Actually,
Good morning, Hannah. Hannah, before you sit down, we do have a couple of handouts over here. One is just the TED Ed questions for today, and then the other one is the next exam, which is a take-home exam.
See, I'm gonna do something, like, I had so many people like asking about what my senior leadership is. And I'm like, well, I don't have money to pay you in my budget.
so basically I have to like
Use my own money and then get like paid
got the budget or whatever. I got like
Okay, we have 8:30, so why don't we get started? Good morning, Psych Stats. Who's ready for a Thanksgiving break? We're there, right? We are there, and I think it's very well deserved that we get a break. So some great news, when we come back on that Monday, you actually have nothing due. Okay, and that was by design. I thought I'd let you have nothing due on that day. And in fact, when you come in, you have our old friend Julie Tucker. Some of you might know Julie from across the way in Doan Hall. Julie does a lot of statistics for Dr. Laurel Kennedy in our student development office. And she's a graduate not only of this class, of this college, but also of this class. She had a psych stats class probably 2010-ish or something like that. So she's going to talk to us about what she's been doing with her statistical prowess in the intervening years. And we'll have her chat with us for about 30 minutes or so. And then we'll take the last 20 minutes to do teaching evaluations that day. Okay? Later on that week, we'll have some time to review for the upcoming quiz. And we'll do some things as ANCOVAs and some factor analysis and some signal detection theory, which we'll do today for the quiz. And then for that Friday, we're going to have our final section exam, which as always will be a take-home section exam, and we'll turn it into a writing workshop for that day. So one of your two handouts for today is that. And I wanted to make sure everybody could also go out, if you wouldn't mind, while we're taking a look at this, could you go out to Blackboard just to make sure you can load all of the articles. And this, again, is not due on Monday, when you come back, but you do have some time, and you might want to take advantage of that time and read some of these articles to help you prepare for the section exam. So if you went out to Blackboard and all the way on down, I want to make sure people can open up these different files, okay, so you can see it all electronically. I have copies of those too on the S drive, but when you're home, it might be the case that Blackboard is more accessible than the S drive is. Okay, so we'll let you go out to Blackboard, down all the way down, and just see if you can open those PDFs. Okay. Meanwhile, we'll just remind you about what's going on in this particular assignment. Okay? In the assignment, we're going to have you try to engage in some integrative complexity. We're going to give you 3 different kinds of articles and ask you to see if you can reflect on the statistics in those and talk a bit about how they might be related across all of this. So it's really the same structure that we had in our most recent section exam. But now we have, excuse me, an article from Dr. Weiss and some of his students from a couple of years ago, some of whom I had in class. And that article focuses on the idea of construct validity in a particular kind of instrument, but he also uses ROC curves for that, okay, receiver operating characteristics. We'll be talking about those today in class. Then, as of about, I think it was Tuesday morning, after I was coming in Tuesday morning, I had an email from the Psychological Science Association, and they have this brand new paper that just came out this week, Replication in Psychological Science. And it's not real long, but it has some really interesting ideas, some of which you've seen before, but I thought that would make a very current and very topical component to our exam. And then a very different perspective, one that we hadn't really talked about, but actually relates in part to signal detection theory. It's called the Bayesian approach to statistics, and it's very different from the null hypothesis testing that we've been doing this time around. So I think it's a nice way to wrap up the semester because it has some advanced statistics, and it shows us some different, almost philosophical takes on what it means to be in statistics. So a nice way to wrap up the course. Okay? The structure, in all other ways, is really the same as all the other exams that we've had in here. Who's all right with all of that? Yeah? Any questions on all of that? Okay, So why don't we jump into where we were yesterday. We'll do just a tad of factor analysis, and then we'll spend most of the day talking about signal detection theory. So if you'll join me in going out to Excel first, we'll get the data set. We'll take a look at the data set, and we're going to do this 3 ways today. This was the factor analytic data set that we had. Out on the S drive in our resources folder, there's a practice set. And the practice set has a subfolder that says factor analysis, and it contains only this one that we've now seen. This is the 3rd day we've seen this data set. And we've talked several times about how this big rectangular structure has 20 variables. And we saw yesterday that they loaded onto 4 components. Okay? So it was a nice way of reducing this complexity in a manner that's consistent with Occam's razor. Okay? So we're going to do that one step again, just to remind ourselves of how we did that, and then we'll take a couple of variations on it, and then we'll go off to signal detection theory. So you'll feel well practiced when something like this comes up on the quiz on Thursday that we're going to have after you come back from the break. Okay? Okay. How many people have this up? If you're able to get to that? Is anybody not finding that? Okay. And we're going to paste that in, just like we did yesterday. If you can make the really, really big rectangle, it goes from H2 all the way down to AA 361, really big rectangle. Okay, so 20 variables times 360 rows. So if you'll now paste those in to SPSS, and I realize it will take a moment for SPSS to come up. Okay, and here are the 20 variables that we see. We'll do just what we did yesterday as a reminder, and then we'll take a couple of variations on this. Bless you. Okay, I'm just going to walk around to see where the systems are. I realize it takes a moment for these things to come up. As we said, when you have really big data sets like the ones that we have, it also takes a moment for Excel and SPSS to talk to each other and get something from your computer's buffer into the SPSS data file. There's sometimes a 5 or 10 second pause because the data set is so big. Okay, I think most of us are there. Okay, I think that's it. How are we doing, Victoria? Is that good? Yeah, I think we're all there. Okay, so if you could remind me about the steps we need to take to perform a factor analysis, and there are different varieties of factor analysis. We're going to do a principal component analysis. We're going to use a Varimax rotation, okay, which will keep our components 90 degrees apart from each other. You wouldn't have to do it that way, but we're going to look for completely independent components. Okay? All right. So you tell me, what are the steps? Analyze this first. Okay. Okay, dimension reduction. Right? We have all of these different variables. We're going to try to reduce them in a way that's consistent with Occam's razor. Okay, and which of these do we want? Factor. Okay, right. Okay. And I was in here a little bit earlier. Let's slide these on over. Okay. We'll slide over all 20 variables, just as we did. And as a reminder, we're going to go to descriptives, and we're going to take a look at coefficients. There are so many boxes here that we could check, but in the interest of time, we'll take only a few. The extraction method that we're going to use is one of several, but we will be using, and on the test, we will only use the one that is principal components, and I think it defaults to that. Okay? We'll look for principal components, and we want those components to be 90 degrees apart from each other, and the name of that particular kind of rotation, as they're described, it's called the Varimax rotation. So we will have complete orthogonality. Okay? And when we have completely orthogonal variables in our geometric interpretation of R, what is the R value associated with that? Completely orthogonal. 0. All right, so we said that correlation is a cosine, and if we took the cosine of 90 degrees, we would be a 0. And the way to think about that is our unit circle. It ranges from positive 1 over here to negative 1 over here. We go up by 90 degrees. We're at the 0 point on the x-axis. Okay? All right, real good. So we can say continue. Okay? And then you can let it rip if you want to let it rip. And it will come back with too many boxes. You can throw away all of the boxes except for the correlation matrix. The total variance explained we thought was pretty interesting. And we also want to take a look at our Varimax rotated component matrix and see what it came up with. Okay? So just to make sure, and just to warm us up this morning, can somebody remind us what goes on here in the correlation matrix? Brief description of that. You had to tell it to a Psych 100 student. What would you say about the correlation matrix? This could be generic, about any correlation matrix. Yeah, thanks.
It shows the strength of the correlation between the variable along the side and the variable along the top.
Okay, really good. Okay, so we're just listing all of the variables here, and we have their R values. The strength of the correlation is kind of nicely explained. Okay, and the intro to psych students really do have correlation. They are able to do R statistics. Many of us do R statistics inside of the intro to psych labs. Okay, can somebody help us out and tell us just a little bit about how we might interpret what's going on in this box? We took a look at this one yesterday, but I walked you through yesterday. Now, you can walk us through today. How do we interpret this total variance explained box? So how many variables do we start out with? 20, okay. And how many are we down to? How many components are we down to? I'll put it that way. We're down to 4, right? Okay. Now this is kind of interesting. If you were to do something like this with, we'll say, personality data, and you put in several hundred different kinds of variables, it might come back out with 5 components, which would be the big 5 that we know about, right? It might be the case that you were able to find that. What SPSS will tell you is here's component 1, here's component 2, 3, 4, and 5. What SPSS can tell you is that the first component is openness. The second component is conscientiousness. The next component is neuroticism. Okay? Those are sort of human-determined words that we think describe what's going on inside of that component. Okay? This is just telling you that statistically, here's something that seems to be orthogonal to this thing, which seems to be orthogonal to that thing. Okay? And it's just going to give you, here are the 4 components, and we're going to call them 1, 2, 3, and 4. They might be meaningful to you in some other way. Maybe one's going to correspond to something like fluid intelligence, and one corresponds to crystallized intelligence. Okay? Those are constructs humans could attach, but here we just have those 4. And we can see 2 things. How much any one component is explaining in all of this variability, and also the accumulation across the different components. And you can see they're building up in roughly in quarters. Right? We're getting something like about 25% of the variance is explained by each of these. Who's okay with all of that? Is that working? Okay. Then can somebody help this hypothetical intro to psych student understand what's going on here in the rotated component matrix? How do we make some sense out of that? Okay, thanks, Gary.
It tells you like how much each individual variable is correlated with the component, so you can see kind of which variables fit into each component.
Okay, right. Okay, so we get to see which particular variables load on which particular component, and that's often the word that they use. And I think one of the reasons why they use load rather than correlation, even though they mean essentially the same thing, is we often talk about correlations between measured variables. So way up top, when we had our first box, we have a bunch of, if you will, correlations. Right? And we'll call them correlations because we're going from one measured variable to another measured variable. Sometimes when you're in conversations at higher level stats and you're talking about many, many different ideas, some of which refer to measured variables, some of which refer to latent variables, it can be helpful to have a separate word that really means the same thing but tells your listener or your reader that you're talking about the relationship between a measured variable and an uber variable, a latent variable. And we call those loadings, but they mean exactly the same thing. And they can be shown exactly the same way geometrically. So they really are correlations, but we call them loadings. Who's okay with that? Yes, please.
So I don't know if it's just because this like data set is like probably ideal, but are the variables that belong in each component usually that strongly like?
They are almost never that strong. Okay. Well, you know what I did just to motivate this example and give us something really simple to look at in a relatively complex analysis. Back in my Excel spreadsheet, I just took advantage of all the geometry that I could, and I said ahead of time, I'm going to create one variable that looks like this, and I'm going to create another variable that looks, 45 degrees away, 60 degrees away, that kind of a thing. So I deliberately cooked those up And I think I cooked up 4 different varieties, and then I just added some random noise to each of those 4 varieties, and that gave me a total of 20 variables that loaded on what I knew would be exactly 4 components. Yep. So yeah, you would never see a real data set like this. Okay, all right. And that so far, are we doing okay? Is that working for us? Why don't we pick up on Gwen's point, and why don't we go with some complete randomness in our data set? So let's do the same thing one more time, but can you join me out in Excel? We'll take 2 of our 20, maybe the first 2, and we'll just turn them into entirely random numbers, and we'll see if we still get a 4-component output over here, or if we get something else. Okay? So we'll all do that together. Can you join me back here in Excel? We'll be in the factor analytic bit. Okay, let's go to the green columns. And just to remind you, as you're making your way back over there, I set this thing up by putting in, if you will, phony degrees. I just numbered from 1 to 360, so I have degrees in this column. I took the cosine and the sine of those, and then I added 45, 60, 30 degrees. And over here, I'm sort of taking advantage of all those columns to get orthogonal measured variables that I know are going to load on these differently colored latent variables. Okay. How many people are back in Excel? Is that working for us? Okay. So you can see that what I've done here is, if you'll join me in cell H2, okay, I'm deliberately referring to this cosine thing, and then all the way down that list, I'm referring to a cosine. Okay, so that this blue group over here is going to be the sine group, this is the cosine group, so I know those are going to be 90 degrees apart, right? And then I just added some random noise on top of that. Why don't we change the first 2 variables in this to make them just completely random? So if you'll join me in H2, let's just get rid of all that stuff, if you would. You can just backspace out of it, and we'll say equals rand, left and right paren. Can somebody remind us what that does? Equals rand, left and right paren. It's been a little while since we used it. It's kind of like rand between.
I think it's for 0 and 1.
Yeah, between 0 and 1. It's a uniform distribution, a flat rectangular distribution. Excuse me, generates some number between 0 and 1. So I'm going to hit go. I'll hit enter. Okay, and I get a random number that's going to be different from yours. Can we do the same thing over here for variable 2? Just for fun. We'll make that equals rand. Okay, so now the first 2 of 360 values in variable 1 and variable 2 are entirely random. They don't bear any relationship necessarily to this cosine variable that we have. So we did those on the 2. If we can highlight those 2, grab that little box on the right-hand side and pull it all the way down to the remaining 359 variables, or I should say levels of this variable. All the way on down. Okay? And now yours are going to be different from the person next to you. Yours will be different from mine. If you hit the F9 key, we'll get all kinds of random variations. Okay? So I'm hoping that that alone might have been enough to disrupt what Gwen correctly pointed out was an ideal data set, right? I cooked the books here so that we would have exactly 5 of these load on factor 1, 5 on factor 2, 5 on factor 3, 5 on factor 4. That got us to 20 variables on 4 factors. I'm actually not sure what's going to happen here, but I would be a little bit surprised if we had such a beautiful loading, right? Maybe another factor will emerge. We'll see how this goes. Okay, so one more time, can you join me by grabbing this huge rectangle that's almost exactly the same as it was a while ago, but now it's only 18/20ths similar to what it was last time because we threw away 2 of the 20 variables. Okay, we'll highlight all of that. We'll go over to SPSS. We'll open up a new data sheet, if we can, in SPSS, and we'll paste in these, excuse me, including the random variables. So let's go to here. I think we can do File, New Data. That just gives us a new data set. And I'm going to do Control-V as in victory. And it does take about 5 or 10 seconds to paste all this in. I don't think mine went. I'm going to try it one more time. Okay, how many people have theirs pasted in? Did that all work? Okay, mine finally showed up here. A little bit of a delay. Okay, let's get some practice. You tell me one more time. How do we get there? Everybody? Analyze. Dimension reduction, factor. Okay, and I think it's all, oh, we do have to slide these 20 in. I don't know if it will retain what we had earlier, but just in case we'll go to descriptives. It didn't. We'll put in coefficients. The extraction method seems to default to principal components, which is really good. And rotation, we want the varimax rotation, so we're looking at factors that are 90 degrees apart from each other. We'll let it spin when you're ready to go. And hopefully that was enough to maybe change our output. Let's get rid of some of the things we don't need. We don't need the active data set. We don't need the communalities. We don't need the component matrix, but we do want the rotated component matrix. Okay? So here are the correlations. And I think I see some good news here that that might have been enough to throw off the otherwise perfect bit, the perfect analysis that we had. Okay? Let's go down to the total variance explained. And first, what did we notice that's different about this? If we look at the cumulative percent explained. Does anybody recall how this one is different from what we had the last time? Yeah, thanks. It's a little bit lower, right? We were explaining it, and we might even have it, maybe you still have it in your output. If we go to the earlier total variance explained, it was almost perfect, right? We were explaining 99.899% of the variability, right? Now that we threw off two of these measured variables, and we go to the total variance explained, excuse me, pardon me, now we're explaining 95% of the variance. So that's still pretty good. This still is quite unrealistic, right? But at least now we've shown that we can get data that are slightly more realistic by adding, as you would expect, random variability to one of your measured variables. Something else that makes this one different from the other one. 95% versus 99% of the variability explained. Something else? There's 5 components rather than 4. So those 4 are still basically loading on each other, okay? And then it's also saying there's this other one that's sticking out, okay? And that's interesting too, because if you look at the first 4 components, they're explaining something like, the first 3 are explaining something like, 25-ish%, okay? And then the fourth one used to explain 25-ish% or thereabouts, and now we've knocked that one down, okay? And we have the emergence of a 5th component that isn't explaining very much variance. It's only explaining about 5% of the variance, okay? Who's following that? Is it working okay for us? All right? Okay, can we, just for kicks, can we try it one more time? I've never done this with the class before. Can we go back out? We'll do the whole thing one more time. But now let's take all 20 variables, all 360 rows, and make everything random. Okay? So now we've gone maybe to the other extreme, and rather than having these perfectly geometrically situated vectors that are orthogonal to each other, we'll go back into Excel and we'll turn the whole ball game random. And I have an idea what this will look like. I'm thinking it'll look like noise, but we'll see. So what we had for we can even do it this way, I think. We can probably grab one of the 2 columns that we had and just pull it over until we run out of real estate over here. And sorry, it's going to turn everything green, but I think that's okay. If people were able to do that, you can grab like maybe column 2 or column 1 and just drag it horizontally over, and now we've got 20 variables, 360 rows, and everything is random. You can hit the F9 key a bunch of times, and just do that quickly. We have equals 20 times 360. I should be able to do that in my head, but that's 7,200 data points are here. Okay? Can we grab all of that? It's a big, big grab, because we have a lot of measured variables there. Okay? We'll do a Control-C to get the ring around the rosy going, and we'll paste this one last time. This will be our final run here on SPSS factor analysis. Okay, and we'll open a new data set. File, new data. We'll paste those in. Okay, I think they're all in. When you're set, you can go ahead and run this. So as we've done a couple of times already, analyze. We're going to do dimension reduction, factor. Okay, we'll slide over these 20. We'll add the coefficients. The extraction method defaults to principal component. We want 90 degrees apart. That's the varimax rotation. We'll spin it. Okay? And we'll throw away some of the unnecessary boxes. There's already too much to look at for our purposes. We don't want the components matrix. We want the rotated components matrix. Okay? Can somebody tell us, well, let's go to this box. What do we see in the total variance explained? We can explain 100% of the variance if you allow us to have 20 components. So we started out with 20, and after we reduced this thing, we wound up with 20. Okay? How many people are following that? That wasn't much of a reduction. Why was it not much of a reduction? I started out with 20. We tried to reduce it. We clicked on reduce, right, or factor reduction. So these are all entirely random. They bear no relationship to each other. Right? So you would expect that you're not going to have all these independent vectors loading on any one thing other than itself. Everything's correlated with itself, but it's not really correlated with anything else. Okay? So we're cheating a little bit here. You might remember that when we did polynomials and we did nonlinear curve fitting, you can always explain, for example, a 9-point data set by having an 8th order polynomial. But that's a really complicated polynomial. Right? You get to have one estimate for every one of your data points. So it's kind of like cheating. Okay? And then we can look really at what we see here. You can see that they've divided this now into 10 on the far right-hand side, extraction, sums of squares, and so forth. But cumulatively, we're not explaining very much. 63% of the variation is being explained. And yeah, 10. It took us 10 variables to get there. Right? So we're not doing very much there. So I think the real information is in this column, where we have 20 factors on which our 20 variables are loading. So two extremes. Right? We're explaining essentially all of the variance in the one case with just 4, and now we're explaining all the variance, but we need all 20 in. Who's okay with all of that? Yeah? Okay. All right. Why don't we put factor analysis away for now? Okay, it'll come up again on our quiz. And why don't we spend our time now going back over to signal detection theory? Okay. So we had a TED Ed on this one, and some people in the class had done this TED Ed way back when, but most of us were doing it for the first time. Okay. So we have our PowerPoint associated with this, and we had our video associated with that. And we learned about Libby and Connie. Why are they named the way they are? Can somebody remind us why Libby and Connie are named the way they are? Preferably somebody who isn't in the S&P class. Okay, thanks.
Because Connie is like the conservative response bias and Libby is like
Oh, right. Okay, so we do have liberal and conservative response biases, right? And this is an important component in ROC curves, which would be one of the items on your exam for the Friday when you come back. And it's also going to rear its head inside of Dr. Weiss's article, which we were going to read for that Monday, but we're not going to be reading that for that Monday because Julie is coming in to chat with us instead. Okay? So we'll get to talk more about the ROC curves in just a little bit. Can somebody help us out with the distinction between a type A experiment, what that means? Yeah, thanks.
So type A experiment means there is a correct and an incorrect response.
Okay, right, yeah, and that's often the case in certain areas of psychology that we have factually correct answers or incorrect answers. In other areas of psychology, we're looking for the qualia, we're looking for the subjective experiences that we have, maybe with colors or sounds or with emotions. But here, we're looking for something that has an objectively, verifiably correct or incorrect answer. Right? Can somebody help us out with a catch trial? What do we mean by a catch trial in signal detection theory? Okay, thanks.
The participant is told to make a response, but there's no stimulus present.
Right, okay, so maybe there's no stimulus there and they have to figure out, they still have to tell us that it was there or that it wasn't there. Otherwise, you can have somebody just saying, oh, I heard that. A related idea, and this will harken back to the inventory that Dr. Weiss had been creating and evaluating with ROC curves. You might remember something like the Minnesota multiphasic personality inventory. Does anybody remember hearing about that? Yeah. So lots of questions on there, and it's used for clinical diagnoses. And there are some questions on there that are essentially catch trials, even though catch trials here are introduced in what we would call a psychophysical context that relates to S&P. You can have catch trials on a personality inventory or on a clinical inventory, and you might give some relatively outrageous statements that somebody who wants you to believe maybe that they've got schizophrenia, or they want you to believe that they've got depression, would say yes to. But most patients who actually have schizophrenia or depression would not endorse. Right? So you can say something about, oh, on a regular basis, I see pink elephants floating around the room. And that's your question. And somebody who wants you to believe that they are suffering from schizophrenia might endorse that question, when in fact, if you look at people who really do have that, they never endorse that question. So there's essentially a catch trial there too. And lots of clinical and personality inventories have something like a catch trial, just like we have here in the psychophysical example that we developed inside of the video. Okay? All right, the two different kinds of errors that we have in signal detection theory. Let's yell them out. I think it's that easy. False alarms and misses, right? They're basically type 1 and type 2. Okay, and the two different kinds of correct responses that we can have. Hits and correct rejections, okay? And then we had you use draw to draw a few things. We won't go there just now. Okay, we have type 1 and type 2. I think this group is pretty good on that. I do want to go to question 8. In your own words, explain how D prime and beta differ from each other in signal detection theory. Those are the primary components that we pull out of signal detection theory. So, okay, thanks. We'll go with an S&P student.
D prime is the person's sensitivity to the stimuli that's presented, and is the person's tendency to favor a certain response.
Okay, right. Yeah, so those two are actually different ideas. Libby and Connie could differ with respect to beta, right? They have different kinds of biases, but they might, at least in principle, have identical biases. Getting back to our MMPI example, we can see how good a particular instrument is at really picking up who has schizophrenia and who doesn't, who is suffering from major depressive disorder, who is not. And you can imagine that a particular instrument might have a bias one way or the next. An instrument might be biased in such a way that it maybe overclassifies people who are responding, such that it suggests that people who don't have schizophrenia, maybe that they do have schizophrenia, right? So it's kind of like having a false positive, and you could skew it that way. That would be a liberal skew in that particular case. You could have a conservatively skewed, conservatively biased MMPI that tends to maybe underclassify, right? It underestimates the probability that you actually have that particular kind of diagnosis. Who's following that? Yeah, okay. So you can see how even though it's introduced here in a S&P context, it has much broader kinds of applicability. Okay. So here's a very S&P question that I think we can skip over, the three different kinds of neural activity. I have a fascination with that because I like neuroscience, but I'd rather go ahead to question number 10. Can we explain what the criterion means in signal detection theory? What does the criterion mean? Okay, thanks, Melanie.
So I answered this a long time ago.
Yeah, it's been a while.
I said that it's sort of a way of like converting underlying neural activity into a behavioral response, and it like sets a boundary so that any level of neural activity higher than the criterion will promptly guess response, whereas when the level of neural activity is below the criterion, the person will likely report that they did not detect it.
Okay, very, very nicely stated. You can also think of it as this. It is an evidentiary boundary. It is an evidentiary boundary. And in the case of signal detection theory as applied to psychophysics and sensation and perception and so forth, we're looking for some kind of evidence. Maybe we're looking for sensory evidence. Okay, if you're a clinician and you're trying to figure out how do I begin to classify this particular set of observations, I'm going to be looking at the evidence that I have, and maybe if I accumulate a certain amount of evidence, I'll say, okay, now I have enough evidence for the diagnosis of ADHD or schizophrenia or obsessive compulsive disorder or PTSD, whatever that evidence is, but we have some kind of a boundary. And you can imagine that different kinds of instruments, different kinds of therapists might have different evidentiary boundaries, where some people are more inclined than others to give that classification. Okay, and that gets us to this idea of having a relatively liberal bias or a relatively conservative bias. Okay, now I think what I want to do is basically stay with the TED-Ed questions roughly, but I also want to look at some of the pictures in the PowerPoint that you had for this class, but the folks in our S&P class didn't have. So here's our criterion. Okay, let me go back just a little bit. Go to a picture that has our criterion in it. And it's setting a boundary. Here we're looking for some level of neural activity. If you're beyond this side and you have a lot of evidence for a stimulus, you would say, yes, I see it. If you have less evidence, you would say, no, I don't. Libby and Connie are going to differ from each other. Libby's down here on the left-hand side. She doesn't need very much evidence for her to say, I think I've got enough evidence to say yes. Connie is much more conservative. She requires a higher level of evidence. Okay, so this thing's going to be moving back and forth. Okay. Now, what I thought I'd like to do is pick up on something that Melanie just said. You and I, as psychologists, often only have access to behavior. Behavior is empirical. Frequently, we're trying to draw an inference from behavior to go into some conclusion about maybe how the nervous system is working, or some conclusion about how this person should be classified on some psychological disorder. So we have only their behavioral responses, but taking advantage of this kind of a layout, we can probably draw all kinds of important inferences. Okay? So what I'll ask you to do, and this is just a little bit subtle in the video, is notice that there's a top row where the stimulus is absent. There's a bottom row where the stimulus is present. And we're going to take that top row and we're going to put it into the top third of the next slide. We're going to take the bottom row, put it into the second row of that next slide, and away we go. So here, I should say it slightly differently, we have just what we had a moment ago. I'm going to rip off this left-hand distribution. I'm going to place it here. I'm going to rip off the right-hand distribution. I'm going to place it right here. Hopefully you can see that they're situated left and right of each other. Okay? And I'm going to draw that line straight on down here. But here, the stimulus was absent. We had only noise. And yet we said, yes, I see it. And when the stimulus is absent and we say, I think I see something, we're false alarmed. So hopefully, people can see a correlation and an association between what's going on here in this diagram and what's going on here in this. Can people see that correspondence? Is that really clear? So this is what you and I as psychologists typically have access to. But we frequently want to draw inferences beyond that. So we go from here and we assume this kind of a arrangement. Okay? And then, just to look at the next couple of slides, we can go with exactly the same data, but we're just going to move the criterion to our left, as Libby would have, and we're going to move our criterion to the right, as Connie would have. Okay, we're on that side. Okay? But the underlying distributions are still equally far apart. This is very much like Cohen's d. Right? Cohen's d was how far apart in standard error are the two means. So d prime is very much like a Cohen's d. It's a measure of effect size. Who's following all that? Okay, now this is where we get just a little bit subtle, and this will be entirely new also for the students who are in S&P. So we go this far in S&P, but we don't actually do computations. But this is a stats class, so we want to now see if we can put together some of the computations. You might notice that I've got some of this stuff cooking over here. I have a 0.5 over a 0.5 on one of the slides. Okay, this is the neutral slide. And just to make sure that we're all okay with this, can you help me out with that mental math? 0.5 divided by 0.5 is equal to 1. Okay, hang on to that number 1. This is the neutral criterion, and it's going to turn out to be equal to 1. Just to show you where that is coming from, if you can imagine that I have a probability axis over here, and this is a low probability, we might call it 0. This is a high probability, we might call it 1. We can look at the probability associated with the intercept of this criterion and a given one of the distributions. So here, this criterion is intercepting the left-hand distribution at about here, and I'm going to cheat and call that 0.5-ish. And over here, we have another intercept at exactly the same level at 0.5. And the typical requirement is, if you want to compute a value for your criterion, you can ask, what is the probability associated with the criterion level of neural activity, in this case, for the right-hand distribution? That's a signal plus noise distribution. So this one winds up in our numerator. We take this guy, that's a 0.5. I'm going to put him over here. That's where that 0.5 came from. I'm now going to take over on here, the left-hand side, that also has an intercept of 0.5. So I get 0.5 over 0.5, and I'm now completely neutral. I have a criterion of 1. If I now pretend that I'm Libby, and I go to the next slide, what happens is, in this particular case, I have something that's not quite so equal in these two, right? I have instead a higher value for my left-hand distribution than I do for my right-hand distribution at criterion. Okay? Sometimes people have trouble seeing this. I want to see how many people are following me. And I'll point it out. Okay? So if we play this rule, we're always going to make our computation for criterion the probability associated with the signal plus noise distribution. That goes in our numerator. And then the corresponding probability for the noise distribution at criterion. That goes in our denominator. So now I'm going to pretend this is 0.6. Okay? And that's going to be in our denominator. The right-hand distribution is always in our numerator, and that's lower than the other distribution. I'll call it 0.2. So can you approximate what is 0.2 over 0.6 approximately? 1/3, okay? So now instead of having a criterion of 1, we have a criterion of 1/3. Libby on the left with low criteria. She has a lower criterion expressed this way, and we can actually get a quantity associated with that. Yeah? Okay? All right. All right. So one more time. We're going to play the game one more time, but now we've seen the neutral one, which is 1. Okay? There's no particular bias here. Now we have a lessened bias. We can come over this way. The criterion is numerically less than it used to be. Let's play the game in the opposite direction. Let's go to Connie. And now we have basically the complementary set of conditions. The criterion is now to the right of center. We're demanding more neural activity before we say, yes, I see it. So we're relatively conservative in our evidentiary boundary. Okay? And our rule was we're going to take the likelihood, or the probability, associated with the right-hand distribution at criterion, 0.6-ish is what I'm approximating here. And then we put that over the corresponding number for the noise-only distribution, which is 0.2. Can you mentally do that math with me? 0.6 over 0.2 is 3. Okay, so now we've computed 3 different criterion values mathematically. The first one was neutrality, and that was 1. As we go less than 1, then we're having a liberal bias. As we go more than 1, we're going to have a conservative bias. And in just a moment, we'll learn some Excel commands to figure out how you can literally pull these numbers out of a Gaussian distribution. Okay? Before we do that, let's take a peek at this kind of a deal, which is actually not inside of your video. Okay, so this is something special for the stats group. Okay, this is called a receiver operating space, and we're going to look at receiver operating characteristics. And this is something that you'll read about in Dr. Weiss's paper for exam 4. So here, this should be fairly simple. You and I have access to the proportion of false alarms that we can empirically observe. These are when the person is saying, yes, I see it, and in fact there wasn't some stimulus there. This is a catch trial. Right. And then when the stimulus actually is there and they tell us that they see it, we have the proportion of hits. So for Shelby, I can say, well, Shelby had this many false alarms and she had that many hits, so Shelby's landing right over here. And Victoria had this many false alarms, but that many hits, and she's landing right over there. Okay, so I can put any given person on this space, and I can come up with a very interesting line here where d prime is equaling 0. So on this primary diagonal, okay, if I go here, somewhat arbitrarily, I have, if you will, a 50% hit rate. I also have a 50% false alarm rate. So I'm as likely to say, yes, I see it when it's there, as I am when it's not there. So d prime should equal 0. I have no discriminability. Right? I actually can't tell how, whether there is a stimulus there, at least not beyond chance. And some people who are very liberal are going to have lots of false alarms, but they're also going to have lots of hits. Okay, Libby will be in this case. Our conservative friends will have many fewer false alarms, but they'll also have many fewer hits. But all these folks on that line, no matter how liberal they are or conservative they are, they're going to have d prime equaling 0. Who's all right with that? Okay, so there's no distinction between those underlying distributions. Okay? Now, this is something that we hadn't seen in the video. Anybody who lands along this curve will have d prime value equaling 1. One way to think about that is the underlying distributions are 1 standard deviation apart from each other. Okay? Right, so anybody who lands anywhere on here will have that, and this is what I think is most fascinating. I love this about the stats. Let's just take 3 tennis balls, we'll put them on here. These correspond to 3 different people. We'll say that the one over here, and the center of these 3, is neutral. Okay, we'll call that person neutral nester. It doesn't have a bias left or right in this particular case. Okay? Let's take now 2 other points. We have one over there, and we're taking the tangent of that point. How many people have done that before? You've taken the tangent, maybe in a calculus class, right? You find sort of the instantaneous slope. Okay? So if you'll play along with me, when you look at the instantaneous slope there for my neutral point, right? That's a slope of about 1. It's pretty parallel to this line. Yeah, okay. Is this slope steeper than 1 or less steep than 1? Steeper, okay? So it would have a slope greater than 1. It would be corresponding to a criterion greater than 1. Okay? So this is actually the point that we would expect for Connie. She has a relatively conservative response bias, and I'll flip back over here. Connie had a relatively conservative response bias. Remember that when we computed her values over here, she had a value that was greater than 1, greater than neutrality. If we plotted her in ROC space, receiver operating characteristic space, she would look like this. Okay? She's still at d prime equals 1, just like me and just like Libby, but she's down here, and what I think is fascinating is the slope of that line is proportional to the ratio of those two likelihoods that we saw a moment ago. Right? We have the likelihood associated with the signal plus noise distribution at criterion, and the likelihood associated with the noise-only distribution at criterion. And then finally, over here, let's take a look at Libby, who's over there. And does Libby have a slope greater than 1 or less than 1? Less than 1, and we said that her criterion was less than 1. Okay? So the slope of the line that you see here is proportional to what we would have computed if we somehow had these probabilities available to us. And if we could somehow pull these probabilities out. Okay? Now, we can also have people who are differing from each other with respect to d prime. Here's d prime equals 2, d prime equals 3. So people can land on different d prime lines. That tells us about their sensitivity, as I think Melanie mentioned. And they also land on different points on a given d prime line that tells us about their bias. Right? It tells us how they're biased, relatively conservatively biased on this lower end of this particular layout, or relatively liberal biased, or they might be dead center-ish and have a real good approximation of neutrality. Who's following all that? Okay, so that's something we don't do in over in the S&P class. We don't actually compute these things. We work with the concept. Okay, this is kind of interesting. Some idea about what's going on in the lower half of this? So we know that was d prime equals 1, 2, and 3. What's going on in the lower half of this diagram? They seem to be doing worse than d prime equals 0. Okay, these folks can have negative d prime values. So instead of the distributions being like this or this or this, they actually begin reversing, weirdly enough. And one of the ways of thinking about this is if you've got somebody who's out here, every time that the stimulus is present, they'll tell you that it isn't there. Okay? And every time that the stimulus is absent, they tell you that it is there. So they're actually doing way worse than chance performance. Okay? We call this the area of the contrary observer. When I say yes, I mean no. When I say no, I mean yes. If you do that consistently enough, you're going to do worse than a person who would have just been responding by chance. Now, if you can imagine having a blind person in this experiment, they would be correct 50% of the time just by chance. So to be worse than chance in a statistically significant manner, you'd have to be making contrary responses. Who's following that? Yeah, really, really interesting stuff. Okay, so let's take a look at a couple of numbers that we can use to work with these distributions, and we've seen some of these before. Okay, so what we're going to wind up doing is seeing this relationship that we saw before when we talked about z-scores between percentile rank, z-scores and probability densities or likelihoods. Okay, and the d prime formula is z hits minus z false alarms. Can we all say that together? Z hits minus z false alarms. It's kind of like French, right? Okay, so z hits minus z false alarms is what we have, and we would use the norm in function. Who remembers using that one before? Yeah, okay, it's been a while. So the normal distribution is the Gaussian distribution, and we're going to stick in a proportion that we can get from our simple stimulus response matrix. We know that Shelby had a 20% hit rate, and she had a 5% false alarm rate. Okay, so we can stick in a proportion, and we get out a z-score. Okay. And then we can do that for hits and false alarms, and we can subtract those two from each other, and we would have Shelby's d prime. Okay? If we wanted to get Shelby's beta, we would use a similar but still distinct kind of Excel command norm dist. We'd say equals norm dist, and we would input now a z-score that we might have gotten from the norm in function. So we take, for example, Shelby's z-hit value, we stick that in, and we come out with some kind of a so-called density or likelihood. And we can do that for her hits, we can do that for her false alarms, and we now take the ratio of those two probability densities, just like we did a moment ago with 0.6 over 0.2, or 0.2 over 0.6. right? Okay? And we can figure out where is Shelby, for example, relative to 1. If she's near 1, she's about neutral. If she's lower than 1, she's relatively liberal. If she's higher than 1, she's relatively conservative. And we can think of where that evidentiary boundary is, or we can also think about where Shelby would be lying on a given d prime curve, relatively lower here with a steep slope, or relatively higher there with a shallower slope. Yeah? You okay with all of that? Okay. All right. All right. So we are just about out of time, and I was going to bring us over to Excel and we could try a couple of the exercises, but we will need something to do for Wednesday when we come back from break, because Monday is already booked, and we'll take that opportunity to do some quick Excel exercises in signal detection theory. We might remind ourselves at that time about ANCOVAs, maybe a little bit about MANOVAs, factor analysis, and that should keep us plenty busy for the following quiz. All right, thanks for a great session. I look forward to seeing you when you come back from break. Okay. Hope you have a restful and safe break. Enjoy.
Oh, maybe I should take this. Page and a half. Like, it has a certain point where I was like, well, I don't have anything tonight. I can't really add another line. I'm a family besides writer, so, like, there comes a point on that where I'm like, I'm going to sound super redundant if I just keep going. Yeah.
It's gonna be a lot easier to listen.
Yeah, because like, our issue did not come for planning, it came with the implementation. So it was like, well, I can't talk about that.
Did you guys actually get it in the
Publishing is really free. The last time I actually looked at it was